Hello and welcome to another Doppler lecture. Okay, I hope you have enjoyed the previous lecture and you have understood all of this about the Doppler equation. But today we're going to go over something pretty interesting that we call aliasing. And the aliasing is an artifact. And as an artifact, it's something that we don't like. Even though there are some good artifacts that we prefer to find and they give us some information, especially when we're working in ultrasound. So aliasing it's a bad artifact because it will position the peak systolic velocities in a place where they don't give you any information. But sometimes aliasing is not bad at all because it tells you that there is a high velocity in an area that that you need to know that there is a high velocity in there. Let me explain this a little bit better. When you're looking for stenosis in the area of stenosis based on the hemodynamics knowledge that you already have, the velocity is high. And then when you place your color box and you do your color Doppler analysis, then you see this aliasing that tells you, hey, there's high velocity. Yes. And also it happens when you use your pulsed wave Doppler and you try to measure the velocity here, it will give you aliasing. The other two modalities for Doppler that we're going to go over, I'm talking about continuous and power, they do not give you this artifact, and that's something that we're going to learn further. Well, aliasing is an artifact. An artifact is something that shows up in the image, which is not real. And as I said before, we have some good artifacts, we have some bad artifacts. Aliasing is like, it's a bad artifact because it doesn't give you the proper information for the peak systolic velocity, but it's not bad at all because it tells you that you have an area of high velocity. And that's pretty useful when you're looking for, that's very useful when you're looking for stenosis. You're looking for stenosis. So aliasing, let's go into this and let me show you the way it looks like. So let's go in here. Alright, so as I said before, we may have aliasing in pulsed wave Doppler, which is this one right here. So pulse wave Doppler in here, and this is the aliasing. And what happens is that your system sets a limit for the peak systolic velocity. Let me tell you something. This limit for the peak systolic velocity that should go up here is adjustable. All right, and then at this time the limit, this is the limit in here. So what your system is going to do is kind of cut in this peak systolic velocities, and those peak systolic velocities are going to be positioned below the baseline. All right. Well, what about if we increase that limit? Then those peak systolic velocities that are below the baseline, they will come back up. They will come back up, and the wave is going to be fixed. Okay, that makes sense, right? That makes sense. So we have a limit. Think about a ceiling and the floor. This is the floor right here, and then we have the ceiling up here. If the floor goes up, all right, that floor, we call it the baseline, then you're going to have less space for this waveform, and of course your system is going to cut those peaks. Okay? Or if the ceiling is so low, then of course the peaks, they're going to have a space, they're not going to have a space, and those peaks are going to be positioned below the baseline. So either you have high floor or low ceiling, or maybe a tall waveform that doesn't fit into this space. It makes sense. That's the way aliasing is going to look like in pulse wave, like this. And let's take a look the way aliasing is going to look like in color flow. So right here. So, you know, we have this color, which is red, and you're going to see like a blue inside this red. So this blue means that this is an area of high velocity, and therefore your system is going to represent it this way. So when we start going over color flow, you are going to really understand why you have this blue inside this red. And why this arrow in here is pointing this way. It's like saying, hey, we're supposed to have this red, but then we have this blue. Okay? So, and, well, you know how aliasing looks like in pulse wave. And you know how aliasing looks like in color flow Doppler. Alright? Now it's time to go deeper into this. You know, as an artifact, you know the way it looks like. We're going pretty organized, and keep the organization all the time. That's the trick to learn all of this. So, let's talk a little bit more about this. So until now, we have been talking about two terms. You know, the ceiling on top, all right, this ceiling on top, we call it the Nyquist limit. Nyquist limit, that's the ceiling. And we have been talking about this wave form, you know, in this wave form is what we call the Doppler shift. And you know this, it's the Doppler shift. So the Nyquist limit, how do you get it? It will be the pulse repetition frequency of the Doppler signal divided by 2. And this pulse repetition frequency has another name. We call it the scale. And please do not confuse this pulse repetition frequency of the Doppler signal with the pulse repetition frequency of the ultrasound. Both are different. Remember what I told you in the beginning of this lectures? It's like if you're having two different machines in one. The ultrasound has its own pulse repetition frequency, which is basically determined by the depth of view, and the Doppler has its own pulse repetition frequency, which is the scale. All right. Now, you know, if you divide the pulse repetition frequency of the Doppler signal by 2, then you're going to have this Nyquist limit. And pay attention to this. If the Doppler shift goes over the Nyquist limit, so one more time, if your Doppler shift goes over the Nyquist limit, then the result is going to be aliasing. And remember, your waveform is going to position the peak systolic velocities below the baseline, and in the color flow you're going to see this blue into the red or the red into the blue. And as I said before, once we go over color flow, we're going to understand this a little bit better. But for now, don't forget about this. Doppler shift goes over the Nyquist limit, so we're going to have aliasing. Alright, let's see if you understood this. Let's see if you understand this. I'm going to give you a couple of examples in a few seconds for you to solve them. And the first one goes like this. Let's say we have the Doppler shift value is, let's use any number in here. Let's say 4 kilohertz. That's the Doppler shift. And the question is, which of this PRF results in aliasing. Now I'm going to give you different options in here. A, all right, so we're going to say 8 kilohertz. B, I'm going to say 10 kilohertz. C, I'm going to say 12 kilohertz. And then D, I'm going to say maybe 6 kilohertz in here. Okay, I'm going to give you a few seconds for you to solve this. So one more time, the Doppler shift value is 4 kilohertz, and it says which of these PRFs results in aliasing. And remember, if you understand this, that you have aliasing whenever the Doppler shift goes over the Nyquist limit, this right here, then you're fine. Then you're good. Then you understand this exercise. You're going to be able to give me one answer. Okay, let's do that. All right, let's go over this. All right, remember, Doppler shift goes over the Nyquist limit. We're going to have aliasing, and the Nyquist limit is the pulse repetition frequency divided by 2. In this example, I'm giving you one Doppler shift, and I'm giving you different pulse repetition frequencies. And I'm asking you, which of this Doppler shift will give you aliasing? Of course, the one that goes over the Nyquist limit. I repeat this one more time. The one that goes over the Nyquist limit. And for A, the Nyquist limit, A divided by 2 equals 4. It's the Nyquist limit for the first signal, for the first PRF. And then you say, is 4 greater than 4? Well, no. So is 4 greater than 4? Is the Doppler shift greater than this Nyquist limit? No. So A is not the answer. Then we go 10. So 10 is the pulse repetition frequency, and then we need to find the Nyquist limit for this PRF. So 10 divided by 2, we have 5. Is the Doppler shift 4 greater than the Nyquist limit 5? No, it is not. So B does not give you aliasing. For item C, 12 divided by 2, that equals 6, which is the Nyquist limit, and the Doppler shift is 4. Is 4 greater than 6? No, of course it's not. So of course the answer has to be D. 6 kilohertz, that's the pulse repetition frequency divided by 2. It will give you 3. So Nyquist limit here is 3 kilohertz. And the Doppler shift that I'm giving to you is 4 kilohertz. And then you ask yourself, is the Doppler shift greater than the Nyquist limit? Of course it is. 4 is greater than 3. So the answer has to be D. All right. That's a perfect example to understand aliasing, but I'll give you another one. All right. I'll give you another one. Okay, now the question says the following. The pulse repetition frequency of a wave is, let's say, let's use 14 kilohertz in here. And the answer is which Doppler shift results in aliasing. Item A right here, option number 1, we're gonna get 7 kilohertz in here. Option number 2 or B, we're gonna get 6 kilohertz in here. C, we're gonna get 5 kilohertz in here. And D, we're gonna get 8 kilohertz in here. So think about this question. It's pretty similar to the other one. It's just to see the other way around. And the first one, I was given to you different pulse repetition frequencies on one Doppler shift. Here, I'm giving you one pulse repetition frequency in different Doppler shift. So let's take a look. I'm going to give you a few seconds for you to analyze this and, think about the answer. Alright, so let's go this way. I'm giving you one pulse repetition frequency, so you need to find the Nyquist limit for that pulse repetition frequency. So Nyquist limit will be pulse repetition frequency, which is 14 kilohertz, divided by 2. So your Nyquist limit is going to be 7 kilohertz, okay? And remember, whenever your Doppler shift goes over the Nyquist limit is when you're going to have aliasing. Alright, so let's go to the first one. A, the Doppler shift is 7. The Nyquist limit is 7. Is 7 greater than 7? No. So A doesn't work. That's not your answer. B, Doppler shift 6. Nyquist limit still 7. Is 6 greater than 7? No, it is not. So B is not going to give you aliasing. C, 5 kilohertz. Does the Doppler shift Nyquist limit is 7? Is 5 greater than 7? No, it is not. So it's not going to give you aliasing. D, 8 kilohertz. Does the Doppler shift Nyquist limit is 7? Is the Doppler shift greater than the Nyquist limit? Is 8 greater than 7? Of course it is. So D is the one that is going to give you aliasing. Alright, what do you think about this? Just review it, go over this, understand it, it's clear in there, you know what aliasing is, you know the way it looks like, and then you know how is this produced whenever the Doppler shift goes over the Nyquist limit. Okay, but we have to go deeper into this. We have to go deeper into this, and now we're gonna do like a type of maybe a table with 3 columns. So the first one's just gonna say how aliasing happens. Alright, the second column is going to say how to fix it. And the third column is going to say disadvantages, right, of doing the adjustment for fixing this aliasing. So whenever you do something in ultrasound, you gain in one side and then you lose in the other. So when we're fixing aliasing, yes, aliasing is just gonna go away, but sometimes we're gonna have a trade-off. We're gonna have something which is not so positive that is going to happen as a result. So we're gonna say here disadvantage of the adjustment. Well, my handwriting is getting better a little bit. Still needs to improve. But well, I hope you understand what I'm trying to communicate. Even though my handwriting is not so perfect, I'm trying to do my best in here. But well, so the first one says how aliasing happens, how to fix it, and disadvantage of the adjustment. Okay, an nice way to understand this is going backwards and remembering the formula that we use for the Doppler shift. Okay, we say Doppler shift equals 2 times the velocity of the blood times the ultrasound frequency times the cosine of the angle divided by the propagation speed of the sound through the blood. Okay, so that's a good way to remember and to understand all of this. And also we need to know that you have aliasing whenever the Doppler shift goes over the Nyquist limit. Okay? All right, so let's go deeper into this. Okay, remember that if velocity of the sound, velocity of the sound is something that we're not going to touch. That's C. We're not going to touch it because it's a constant value. So we're going to basically focus. We're going to focus in the upper part of the equation. Right? We're going to go over velocity of the blood or of the flow, frequency of the transducer, and cosine of the angle of incidence in here. And it goes this way. If blood velocity, this one right here, increases, then the Doppler shift is going to increase, and then it will go over the Nyquist limit, and there are more chances for aliasing. So number one in here, how aliasing happens if flow velocity increases. How to fix it? Okay, so remember, flow velocity is something that belongs to the patient. So we cannot tell to the patient, hey, can you make the flow in the internal carotid a little bit slower? I cannot measure my wave. Oh, can you make the flow in your mitral valve a little bit slower because I cannot measure this wave? No, you cannot do that. But when the flow is extremely fast, has a high velocity that pulse wave Doppler cannot measure, you have this other option, especially when you're working in cardiac. You can use continuous wave Doppler. And because the wave is continuous, all right, continuous, there is no pulse repetition frequency. And if there is no pulse repetition frequency, there is no aliasing. So continuous wave Doppler is not going to give you aliasing. Never ever. Alright? So disadvantage of using a continuous wave Doppler, one of those is it doesn't have a sample volume. And what is a sample volume? It's something that we call the sample gate. It's a little square. Now we're going to learn later, once we go over this Doppler modalities. It's a little gate that you place with it, whatever you want to place it, like inside the vessel, in one cardiac valve, right? Whatever you place it, it will give you information about that area only, okay? But the continuous wave Doppler doesn't have that sample volume, meaning that if you have your line of the continuous wave and it goes over two structures at the same time, it will give information about the one that is giving you the highest velocity. So which one it is, you don't know. Because what? Because you don't have a sample volume, like specificity of your place where you want to measure the velocity. So that's one disadvantage of the continuous wave Doppler, okay? So there's no sample volume here. So now we will continue breaking down the equation. So next is the frequency of the transducer. If frequency increases, okay, if frequency increases, what happens to Doppler shift? Okay, Doppler shift is going to increase. There will be more chances for this Doppler shift to go over the Nyquist limit. All right, then we have aliasing. So how do you fix this? So nowadays we have these systems, these machines, that the frequency is totally adjustable, so you're able to adjust the frequency. So what you can do is say, well, I'm going to reduce my frequency right here. And the problem is that you start losing resolution sometimes, because remember, low frequency, low resolution. So resolution may be affected. Okay, we're going fine. We're going good. Next, cosine of the angle. All right, cosine of the angle. And if you remember from our previous lecture, the Doppler shift was directly related to the cosine of the angle, but not to the angle itself. The way it works is the following. If you have a lower angulation, then the cosine for that angle is going to increase. And of course that will result in higher Doppler shift that has more chances to go over the Nyquist limit. So if your angulation is small, you have more chances for aliasing because the cosine of the angle is going to be greater. So of course, how you fix this? You have something in your system that you call angle correction. So correct the angle. Increase the angulation now. But there is a problem in here, and don't forget about this. As you increase your angulation and you're getting closer to 90 degrees, the chances for mistakes and measurement errors are going to increase. So be careful with this of increasing the angulation too much. All right? So the problem with going with a high angulation is, not too accurate velocity measurements. Okay, so we will continue. So we are done with this formula here, but we have to add 3 more items. Okay, we're gonna get number 4 with this star sign here, and that will be the scale. If your scale is too low, that means the pulse repetition frequency is too low. And remember, Nyquist limit equals pulse repetition frequency divided by 2. If pulse repetition frequency goes down, Nyquist limit is going to go down. And then there are more chances for this Doppler shift to go over the Nyquist limit. It makes sense. All right? So how do you fix this? How do you fix the aliasing? All right, increase the scale. But there's a problem in here when you increase the scale. If you increase the scale, you start losing sensitivity to slow flow. So we're going to say that the disadvantage in here is that sensitivity decreases. Okay, so beautiful. So we have the scale. So if you increase the scale, the aliasing is going to disappear, but then you're going to start losing sensitivity to the flow. And the magic of this virtual learning is that for my next lecture, I will connect my ultrasound system to this software, and we're going to be able to see all these adjustments, and we're going to be able to see all these Doppler modalities. It's going to be fun. So you can learn at your own pace, and you have all this information for your knowledge. All right. Okay. So number 5, and I'm getting rid of this page in here. All right. I think we're gonna find another. We're gonna open another page. They're not going to disappear. We have plenty of them. This is the digital world. Okay. So it's gonna get number 5 in here. And remember, Column 1 is how aliasing is produced, how to fix it, what's the disadvantage of doing this adjustment. All right, you remember that. So number 5 is how aliasing is produced when you have a deeper view of your vessel. So when depth of view is too deep. When depth of view increases. All right, so if you're going too deep when you don't need it, there's a problem. You know, your sound, your echo will take a longer time to come back to the system. That reduces the pulse repetition frequency of the signal. So now your signal is going to work like this. Boom. 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 Right? So pulse repetition frequency is how many pulses you have in 1 second. And we're talking about the pulse repetition frequency of the Doppler signal, which is going to be affected by the depth of view, where you're getting this vessel information. So of course, if you want to fix this aliasing because the depth of view is so deep, is so increased, well, find a shallower view of the vessel. All right, find a shallower view of the vessel. What is the disadvantage of doing this? We have known nothing. If you change the depth of view, congratulations, you're going to have the aliasing gone from your entire picture. And number 6 will be the baseline. Remember the floor? If that floor is so high, so if we have a high baseline, all right, we have a high baseline here. Let's erase this. All right, if we have a high baseline, then we're going to have less space between the floor and the ceiling. We don't like that. All right. So how do you get rid of the aliasing? All right, so lower the baseline. Now let me tell you something. Sometimes the problem with the aliasing is not because the baseline is so high. The problem with the aliasing is because maybe you have one incorrect angulation, or maybe you have a pulse repetition frequency that is so low. And then you come and fix this with the baseline instead of fixing it with the angle correction or with the pulse repetition frequency that was so low. Now you can increase it. So the problem with the baseline is you still have the problem in there, but you're just like trying to make this waveform to look beautiful, all right? But the problem is still there. The problem was the angle in the beginning. You didn't fix it. The problem was the pulse repetition frequency in the beginning. You didn't fix it, but you selected to fix this aliasing with the baseline, and now your wave looks a little bit better when it comes to aesthetics. You know, looks nice, but the problem remains in there. So be careful with the baseline, because the baseline sometimes what makes us making your waveform to look nicer, but then the problem that gave you the aliasing, on the first instance is still there, right? Okay, so you know, the problem with the baseline is that one. Okay, so be careful with this one. So I'm just gonna type in here, write down hint for, remember, before using the baseline, to fix the aliasing or the appearance of your waveform, fix the mistake that gave you the aliasing for first instant. Alright, and this is what I have for you today. This is our aliasing. It's good to understand this. So we took the opportunity, went over this Doppler equation one more time, so you can understand this. And next lecture for this vascular course is going to be the different Doppler modalities that we have. And next time I'm going to connect my system to the software, and we're going to go over these modalities, and I will take a little time to explain this aliasing. I will provoke it, and I will create the aliasing. I will fix it myself. It will be fun. So I hope to see you next time, and have a wonderful day, and keep studying and learning.